This meeting is being recorded.
This first problem from chapter 3 asks us to take a look at some of these acid-base reactions shown below, and we'll study these in greater detail. So in this question specifically, they ask us to draw the mechanism and then clearly label both the acid and base reactants, and then the products will label as a conjugate acid or conjugate base. So let's take a look at how we can figure out this mechanism and figure out what is our acid, what's our base species. So if you recall, an acid is a proton donor in the Bronsted-Lowry classification, and a base is a proton acceptor. So an acid will give up its proton. So let's take a look here at this first reaction. And if you're unsure of what species is behaving as an acid or base, you can always take a look at the products. So in this case, phenol, this is species over here, this is our phenol, it has lost a proton. So originally we had these two lone pairs. Now we see a -1 formal charge on our oxygen. So we know that there's 3 lone pairs. So what happened with this mechanism? So we know that this was acting as an acid since it donated its proton. So therefore our hydroxide must be working as a base. And we would have that negative charge on oxygen indicates 3 lone pairs. So what happens is one of those lone pairs will grab that hydrogen there, that proton, and then we'll draw a second curved arrow showing movement of the electrons to that oxygen on the phenol. So that's how it has the 3 lone pairs now on the product side. So the acid has a pair or a conjugate with this species over here. So this is our conjugate base. And a water molecule would then be our conjugate acid. It's like the hydroxide, but it has 1 extra proton. So we have effectively now drawn the mechanism and clearly labeled acid-base, conjugate acid. Let's take a look at the second reaction, reaction B here. And once again, we should sometimes draw in our lone pairs to make things a little bit easier to see. Right, so we have some lone pairs on water. So let's take a look at our reagents. So our hydronium here, this species has 3 protons, and then something similar on the product side only has 2. So this hydronium species must be working as an acid. It has donated its proton, and then the water molecule over here would then be the conjugate base to that acid. It's very similar, but 1 less proton. So then we must know that this ketone must be functioning as a base. So we have our base here. And if we were to draw this mechanism, we would grab one of these protons with that lone pair, and then the electrons involved in the bond would then be transferred to the oxygen. And that's where we see our water molecule on the product side with those 2 lone pairs now. So we have base, we have acid, we have conjugate base. So that must mean this is our conjugate acid, and it looks very similar to our ketone reagent, but with 1 extra proton. So that must be our conjugate acid. Let's take a look at C now. And at this point, we have 2 lone pairs on our nitrogen, since it has a -1 formal charge, and then we have these 2 lone pairs on our oxygen. Let's take a look at the products. I think that would be the easiest way to find out who's losing, who's accepting, who's donating protons. So what we see here is a -1 formal charge on this carbon. So that means that that carbon has lost a proton. And we see over here that this nitrogen has received it. So this species over here must be working as our acid. It donated a proton. This species here with the nitrogen must be our base, since it has accepted a proton on the product side. And let's see how this mechanism would work. So we know that there are 3 hydrogens coming off of this carbon because it doesn't have a formal charge, so it must have 4 bonds to that carbon. So one of those lone pairs from our base will grab that proton, and then those electrons involved in the bond will be transferred to our carbon. So that's what we see over here. We see a lone pair on our product side, and this would then be our conjugate base, so our CB. And the nitrogen species, the amine that we see here, this would then be our conjugate acid. It has one more proton than its conjugate on the other side than the nitrogen species that acts as a base. All right, so we have one more mechanism to look at here and determine our acid and base and conjugate acid and base. So we see hydroxide here. We know that it has lots of lone pairs. We have some lone pairs on this oxygen as well, and this one here. So let's take a look. The hydroxide has picked up a proton. So we're going to say this is our base. It has accepted a proton, and this would be our conjugate acid, the water molecule. So then this must be our acid, and we can confirm that over here because that oxygen has lost a proton, so our conjugate base. Now let's see, how does this mechanism work? So we have a lone pair on our oxygen. We'll grab that acidic proton. The electrons involved in the OH bond will be shifted to our oxygen, and then we see on our product side, our conjugate base will then have 3 lone pairs. So these are all of the steps or the mechanisms for these acid-base reactions. And we also see the labeling for the conjugate acids, bases, and our reagents, acid and base.